This screencast goes over heat transfer basics, some of the terms, the modes, and some of the basic equations that govern heat transfer. So let's start. What is heat transfer? Well, first of all, it's energy. It moves from one place to another. The reason that it moves is due to a temperature difference. So this is because of a change in temperature. It goes, as you probably know from your own experience, from hot to cold. So we have three modes of heat transfer: conduction, convection, and radiation. Even though I'm going to give you some of the simplified equations that govern these three modes, in later screencasts we'll talk about some of the complications of these equations. So first, what's conduction? So this is a kind of energy transfer. It goes from more energetic particles, so something of higher energy, to less energetic particles. And the reason that it does this is because of molecular interactions. So it's these molecular interactions that cause the mode of conduction. The second type is convection, and this has two parts to it. The first one is similar to conduction, which is the diffusion or the molecular interaction part. But in addition, it has heat transfer due to the motion of a fluid. And these are bulk or macroscopic effects. And we have two types of convection: forced, which is caused by some, as it says, forced motion, a pump, a fan, something like that; and free, which is caused by density differences. So the final form of heat transfer is radiation. And radiation is energy that's emitted by matter, and this energy is caused by a change in electron configurations. What's different from this method of heat transfer is it doesn't need a material medium. In fact, what it works best in is a vacuum. So let's take a look at the basic equations. And again, these are simplified versions of all three modes. So we're going to start with conduction, and we're actually going to look at conduction in the x direction. This is minus k dt dx, where k is a term called the thermal conductivity. And if you notice, there is a negative sign, and the reason that this is negative is that the Q, or the heat transfer, is in the direction of a negative temperature gradient. What does that mean? That means that this heat transfer is caused by going from some higher temperature to a lower temperature. The next equation we're going to look at is convection. This is H, which is the heat transfer coefficient, times an area, all times a temperature difference. And if you notice here, we have T sub s, which is usually of the surface, and T infinity, which is that of the surroundings. And this is what's known as Newton's law of cooling. And this seems like a very simple equation, but what makes this difficult is determining that heat transfer coefficient. And finally, we have our heat transfer due to radiation. And this is epsilon, which is the emissivity, times sigma, which is the Stefan-Boltzmann constant, times the area, all multiplied by Ts to the fourth, which is the surface temperature, minus T surrounding to the fourth, which is the temperature of the surroundings. And because these are raised to the fourth, temperature always has to be in Kelvin. This emissivity is a property of the surface that the radiation is occurring from. The next thing we're going to talk about are the terms that are important in heat transfer. So Q, which is what we were looking at before, is the heat rate. And this is in units of watts, which is joules per second. So this is energy per time. We also see what's known as the heat flux. And the heat flux is actually the rate of the heat transfer. In other words, Q per unit area. Therefore, its units are watts per meter squared. You might also see Q prime, which is our heat rate per unit length. Units for this are watts per meter. And you'll see, depending on the mode and the situation of heat transfer, that some of these terms are used and some of them are not.